Two galaxies are crashing together in a slow-motion dance of destruction. This is the Antennae Galaxies, a pair of colliding star systems where the rules of normal physics seem to break down. By the end of this journey, you will have explored 50 of the strangest phenomena born from this cosmic wreck. We will uncover how black holes can be flung into the void and why entire star clusters vanish without a trace. What do you think happens when two entire worlds of stars smash into one another? At the heart of this cosmic chaos lies the collision of two distinct island universes. These are not single galaxies, but a pair known as NGC 4038 and NGC 4039, locked in a gravitational embrace from which neither can escape. This merger did not begin with a single, violent crash. Instead, it started hundreds of millions of years ago as a slow, graceful dance, a gentle brushing of stellar outskirts that has since escalated into a full-scale demolition. The immense, invisible hands of gravity are the architects of this destruction, pulling and stretching the very fabric of each galaxy. They have already ripped vast rivers of stars, gas, and dust from their galactic homes, flinging them out into the void to form the spectacular, arching tails that resemble an insect's antennae. This is not a quick event, but a slow-motion rearrangement of entire worlds, setting the stage for all the other strange phenomena yet to come. Within this gravitational storm, a new kind of structure begins to emerge. The same forces that are tearing the galaxies apart are also forging incredible stellar nurseries. Vast clouds of gas, compressed by the immense pressure of the collision, suddenly collapse under their own weight. This triggers a ferocious burst of star formation, a firestorm of birth on a scale almost impossible to comprehend. From this chaos, superstar clusters are born. Imagine not just one star forming, but hundreds of thousands, even millions, all igniting at nearly the same time within a densely packed region. These are not the loose, open clusters we see in our own Milky Way. These are colossal cities of stars bound together by gravity in a spectacular, blazing knot. A single one of these superclusters can be so brilliant it emits more light than an entire small galaxy. They are temporary, brilliant beacons in the cosmic dark, and astronomers believe we are witnessing the very process that creates the ancient, glittering globular clusters that orbit older galaxies today. What does it mean for a star to be born into such a crowded, violent neighborhood? The fate of these stars is our next great mystery. These stellar nurseries begin as colossal, drifting clouds, the raw material of creation scattered across the wreckage. We call them nebulae, and within the antennae, they are not merely present, they are prolific. Each cloud is a sprawling sea of hydrogen and helium, the fundamental elements forged in the Big Bang, now laced with fine dust grains of heavier elements. In a quiet galaxy, such a cloud might drift for eons unchanged, but here there is no peace. The galactic collision sends immense shockwaves rippling through the chaos, like a sonic boom moving through a fog. When one of these pressure waves slams into a nebula, it does not simply pass through. It squeezes, it compresses the vast cloud, pushing the gas and dust into dense, tight knots. Within these knots, gravity, which was once too weak to pull the cloud together, suddenly finds a new advantage. The compressed material reaches a critical tipping point and gravity wins. The knot collapses in on itself, rapidly spinning and heating up until, deep in its core, nuclear fusion ignites. A new star is born. This process is not happening in isolated pockets. It is a firestorm of creation, with shockwaves triggering cascades of new stars all across the merging galaxies. The rate of star birth here is staggering, hundreds of times faster than the gentle, ongoing rate within our own Milky Way. The Antennae Galaxies are not just tearing themselves apart, they are feverishly building anew from the ruins. But what happens to the most massive of these newborn stars? Their lives are spectacular, and their deaths even more so, seeding the cosmos with the very elements that make our own existence possible. But the most massive stars are not the only giants caught in this celestial upheaval. Deep within the cores of the two original galaxies, something even more immense is stirring. Each galaxy likely harbored its own supermassive black hole, a gravitational monster millions of times heavier than our Sun. For billions of years, these black holes sat quietly at the center of their respective domains. Now, as the galaxies merge, their central black holes are no longer solitary kings. They are being dragged toward each other, beginning a dangerous and intricate dance. When two black holes orbit one another, their gravitational interaction is a complex push and pull. But introduce a third massive object, perhaps another black hole drawn in from the chaos, and the dance can turn violent. The three-body problem, as physicists call it, is fundamentally unstable. In this gravitational tussle, one of the black holes can be robbed of its orbital energy. The other two act like a slingshot, flinging the third out into the void at an incredible speed. This is not a gentle nudge, but a catastrophic ejection. The exiled black hole, a supermassive entity that once ruled the heart of a galaxy, is suddenly set adrift. It becomes a rogue, a dark king dethroned, shooting through the lonely intergalactic spaces between galaxies. It would carry with it a retinue of stars tightly bound by its gravity, a ghostly procession fleeing the scene of the collision. The Antennae Galaxies may very well be creating such a runaway behemoth right now, a dark traveler on a one-way journey into nothingness. What would the sky look like from a world orbiting a star in that fleeing cluster? Those spectacular arching streams define the very name of this cosmic collision. They are the antennae, the long tidal tails that stretch far beyond the chaotic central region. These are not spiral arms, the orderly structures you see in a calm galaxy. They are something far more violent and temporary. They are the debris of the collision, vast rivers of stars, gas, and dust that have been literally torn from the bodies of the original galaxies. The immense and invisible force of gravity did not just pull the galaxies together, it also acted like a cosmic tide. As the galaxies swung past each other, the difference in the gravitational pull on the near side versus the far side of each galaxy was so extreme that it stretched them, pulling material out into these long, graceful arcs. The scale is almost beyond human comprehension. Each of these tidal tails spans hundreds of thousands of light years. If you could place one of them in the empty space between our Milky Way and the Andromeda Galaxy, it would easily bridge the vast gap. They are not just a beautiful side effect, they are a fossil record of the entire event. By studying the motion and composition of the stars within these tails, astronomers can rewind the cosmic clock. They can trace the trajectories of the stars back in time to calculate the precise angle and speed of the initial galactic encounter millions of years ago. These streams of exiled suns are a living history book written in starlight, telling the story of the disaster that created them. This relentless birth of stars comes with a brutal consequence. For every wave of new stars, a corresponding wave of death is not far behind. The most massive stars, those born from the densest knots of gas, are the true giants of this cosmic nursery. But their greatness is a fleeting one. They burn through their nuclear fuel at a ferocious rate, shining with a brilliance millions of times greater than our own sun. Yet this profligate spending of energy cannot last. Within just a few million years, a mere blink in cosmic time, these stellar titans exhaust the fuel in their cores. With the outward pressure of fusion gone, their own immense gravity wins the final battle, and the star collapses in on itself in a catastrophic instant. The result is a supernova, an explosion of such staggering power that it can, for a few weeks, outshine the combined light of every other star in its entire host galaxy. And within the Antennae Galaxies, these stellar detonations are not rare, isolated events. they are a near-constant thunder, a fireworks display on a galactic scale. The rate of supernova here is vastly higher than in a typical, quiet galaxy. This is the direct, violent echo of the star-forming firestorm. The most massive stars live fast, die young, and leave a spectacularly beautiful corpse. But these explosions are far more than just a final curtain call. Each supernova sends a titanic shockwave racing out through the surrounding clouds of gas and dust. This wall of pure force slams into neighboring nebulae, compressing them just as the initial galactic collision did. It squeezes the gas, triggering the collapse of new pockets of material and igniting the next generation of stars. This creates a self-perpetuating cycle of creation and destruction. Star birth leads to the death of massive stars in supernova, and those supernova then trigger the birth of more stars. It is a furious feedback loop, a cosmic engine of rebirth powered by its own violence. How long can such a ferocious cycle possibly last before it consumes all the available fuel? Amidst this symphony of creation and destruction, a different kind of signal pierces the cosmic static. Scattered throughout the wreckage are mysterious, intensely bright beacons shining not in visible light but in high-energy X-rays. Astronomers call them ultraluminous X-ray sources, or ULXs for short. Each one is a pinpoint of radiation so powerful it defies easy explanation. A typical stellar mass black hole, formed from a collapsing star, has a theoretical maximum brightness, a limit to how much material it can devour and thus how brightly it can shine in X-rays. Yet these ULXs blast out X-ray radiation that shatters that limit, sometimes by factors of hundreds. They are impossibly bright, like a single candle somehow outshining a bonfire. So what are they? The leading theories are as fascinating as the objects themselves. One possibility is that we are seeing intermediate mass black holes, the long-sought missing link between stellar mass black holes and the supermassive giants at galactic centers. These would be black holes weighing thousands of times the mass of our Sun, massive enough to accrete material and shine with the incredible brilliance we observe. The other compelling idea is that they are stellar mass black holes operating in a rare and extreme mode. Instead of pulling matter in at a steady rate, they could be gorging themselves in a super-Eddington state, a feeding frenzy where so much gas and dust is funneled into the black hole's disk that the radiation pressure cannot stop the inflow, allowing it to break its supposed brightness limit. The chaotic, gas-rich environment of the Antennae Galaxies is the perfect nursery for such bizarre objects. Here, the constant collisions and shockwaves can easily funnel vast amounts of fuel toward a single black hole, pushing it into this extreme state of being. Each of these ultraluminous X-ray sources is a profound puzzle, a point of light that challenges our understanding of physics itself. These brilliant X-ray sources and stellar explosions are all part of the visible wreckage, but they are not the most massive component of this cosmic crash. The true heavyweights of this merger are completely invisible. We call it dark matter, a mysterious substance that does not emit, absorb, or reflect any light. It reveals itself only through its immense gravitational pull. The collision of the Antennae Galaxies provides a rare and perfect experiment for mapping this unseen material. Think of it like this: if you threw a handful of glitter into a fan, the glitter would scatter everywhere, pushed by the air. But if you threw a handful of heavy rocks, they would travel in a straighter line, largely unaffected by the wind. In this galactic collision, the visible stars, gas, and dust are like the glitter. They smash into each other, feel friction, and slow down, creating the spectacular tidal tails and compressed star-forming regions. But dark matter is like the rocks. Scientists believe the particles of dark matter barely interact with each other or with normal matter except through gravity. They simply pass right through the chaos. This means the dark matter halos, the vast, invisible spheres of this stuff that are thought to surround each galaxy, should behave differently than the visible material. As the two galaxies merge, their dark matter halos are predicted to overshoot the visible wreckage. They might even separate from the stars and gas entirely for a time, their ghostly presence lagging behind or stretching out ahead of the light. How can we possibly detect something we cannot see? The key lies in those long, graceful tidal tails of stars. The shape and motion of these streams are dictated by the total gravity they feel, a combination of the pull from the visible matter and the dominant, unseen pull from the dark matter. By meticulously mapping the paths of the exiled stars, astronomers can work backward. They can calculate the precise gravitational field required to create those paths, and in doing so, they trace the outline of the invisible dark matter halos. This cosmic collision has, in effect, become a giant laboratory, allowing us to see the shadow of the universe's greatest mystery. Amidst this chaos of visible and invisible forces, another powerful player weaves through the wreckage an unseen web of energy. Magnetic fields permeate the entire collision, threading through the clouds of gas and the voids between stars. In a quiet galaxy, these fields might be orderly and calm, but here they are anything but. The same turbulent motions that trigger star formation also seize these magnetic fields, stretching and twisting them into incredibly complex shapes. Imagine a pot of boiling water with furious currents churning just below the surface. Now picture dragging a spoon through it, creating swirling vortices that trap and stretch tiny bubbles. The turbulent gas in the Antennae Galaxies does exactly this to the magnetic fields, amplifying their strength and tangling their lines of force into a cosmic snarl. We cannot see these fields directly, but we can trace their ghostly outline by listening to the radio waves they emit. As electrons spiral at nearly the speed of light along the magnetic field lines, they release a specific type of polarized radio emission, a signal that acts like a map for astronomers. This reveals a magnetic environment far more intense and disordered than anything found in an isolated galaxy. These amplified fields are not merely passive observers, they actively shape the drama around them. They can influence how a massive gas cloud collapses, providing a scaffold that supports the cloud against its own gravity, potentially determining whether it forms a few giant stars or a multitude of smaller ones. They also act as giant, invisible conduits, guiding and confining the ultra-high energy particles we call cosmic rays. These fields add a final, crucial layer of dynamism to the merging environment, a hidden architecture of force that orchestrates the flow of matter and energy on a truly galactic scale. What other invisible forces are at work directing the final fate of all this scattered material? Glowing like dying embers scattered across the forge of creation, a special population of stars dominates the landscape. These are the red supergiants, the swollen, elderly giants of the stellar world. They began their lives as some of the most massive stars born in the recent firestorm, true behemoths many times heavier than our own sun. For millions of years they burned hot and fast, a brilliant blue-white. But now, having exhausted the hydrogen fuel in their cores, they have entered their final dramatic act. Their outer layers have expanded outward, cooling as they go, transforming the star into a vast, tenuous sphere. If one were placed at the center of our solar system, its surface could easily engulf the orbit of Earth or even Mars. They glow with the deep, cool crimson of a banked fire, a stark contrast to the hot, blue light of the younger stars around them. Their sheer abundance here is a direct cosmic timestamp, a clear sign that a tremendous wave of star birth swept through this region a few million years ago. These are the stars that are destined to become the supernova we discussed, the very engines that will seed the galaxy with newly forged elements. But before that final, violent moment, they are quietly doing the profound work of cosmic alchemy. Deep within their swollen cores, under immense pressure and heat, they are relentlessly fusing heavier and heavier elements. Helium atoms are crushed into carbon, carbon into oxygen, and so on, creating a layered onion-like structure of newly minted atoms right up to iron. This process enriches the star's interior with the very building blocks of planets and life. When these red supergiants finally do explode, they will blast this newly created material out into the surrounding gas clouds. The iron in your blood and the calcium in your bones were once forged in the heart of a star just like this, before being scattered across the cosmos by a supernova. So every red supergiant we see in the antennae is not just a dying star, it is a future fountain of creation, a promise that from this destruction will come the potential for new worlds and perhaps one day new life. This brilliant chaos is not the final chapter. What we are witnessing in the Antennae Galaxies is a spectacular but fleeting moment in a story that spans billions of years. This cosmic wreck is a living fossil, a single snapshot of a process that will ultimately lead to a very different kind of galaxy. The furious bursts of star formation, the swirling tails of exiled stars, the dueling black holes, all of this is a temporary state. Over the next several 100 million years, the gravitational dance will continue, pulling the two galactic cores ever closer. They will no longer swing past each other, but will instead spiral inward, finally coalescing into a single new core. The fuel for new stars, the vast clouds of gas and dust, will be either consumed in the final firestorm of birth or blown entirely out of the galaxy by the combined winds of supernova and intense radiation. Without this raw material, star formation will grind to a halt. The brilliant blue hues of hot, young stars will fade away, leaving behind the cooler, longer-lived stars. The system will transform into a smooth, featureless elliptical galaxy, a vast swarm of aging stars glowing with a dull, reddish light. Astronomers often call such galaxies red and dead, not because the stars have died, but because new ones are no longer being born. Even those magnificent arching tidal tails, the very features that give the antennae their name, will not last. The stars within them will gradually drift apart or fall back toward the new galactic center, their beautiful streams dissolving into the general haze of the elliptical galaxy. The violence of the collision will fade into a quiet, stable equilibrium. This future galaxy will be a monument to the merger, a calm and ancient entity whose wild youth is recorded only in the motions of its oldest stars. What other secrets of galactic evolution are locked within this single, chaotic frame of a billion-year movie? Deep within the light of this cosmic wreck, a hidden signature glows. Our most powerful space telescopes have detected strange patterns in the infrared light streaming from the Antennae Galaxies. These are not the sharp, clean lines produced by familiar atoms like hydrogen or helium. Instead, they are broad, blurry bumps in the spectrum, like unidentified hills on a map of known mountains. They are ghostly features that cannot be easily explained by the simple chemistry we understand. So what is creating these mysterious emissions? The leading theories point to the incredible chemical complexity born from stellar violence. One compelling idea is that we are seeing the faint glow of vast clouds of complex organic molecules, specifically things called polycyclic aromatic hydrocarbons. That is a complicated name for a relatively simple concept. Imagine the soot from a candle flame, but on a cosmic scale. These are sprawling, flat molecules made of rings of carbon and hydrogen, the same basic structures found in charcoal or in the exhaust from a car. They are not signs of life, but they are its fundamental building blocks. When ultraviolet light from hot, young stars shines on these molecules, they vibrate and emit a distinctive, fuzzy glow in the infrared. Another possibility is that the signal comes from incredibly tiny grains of silicate dust, the same stuff that makes up sand on a beach, but so small they behave differently. The turbulent environment of the merging galaxies is a perfect factory for this cosmic dust. Supernova explosions blast heavy elements forged in stellar cores out into space, where they can cool and condense around these complex molecules or tiny mineral grains. These unidentified infrared features are therefore a direct clue to the chemical enrichment happening in real time. They are a hazy fingerprint of the universe's ability to build complexity from chaos, transforming the simple ashes of dead stars into the potential ingredients for future worlds. This brilliant firestorm of star clusters presents a deep and troubling cosmic puzzle. While our telescopes reveal thousands of these superstar clusters, brilliant knots of light scattered across the wreckage, our theoretical models tell a different story. They predict a far more violent future for these stellar cities. Within just a few 100 million years, the vast majority of them should be torn apart. The gravitational tides from the chaotic, merging galaxy constantly pull and stretch at them from the outside. Meanwhile, on the inside, a different kind of demolition is underway. The clusters are so densely packed that stars are constantly gravitationally nudging each other, a celestial game of billiards played out over millions of years. These interactions can fling the slower, lower-mass stars out of the cluster, bleeding it of its population. The most massive stars, which live fast and die young, often explode as supernova. Each violent death not only removes a massive member, but can also rock the entire cluster with its shockwave, further destabilizing the gravitational glue that holds it together. So where are all the dissolving clusters? Why do we see so many when so few should survive? This is the missing cluster problem. One possibility is that we are simply catching this merger at a perfect, fleeting moment, a snapshot in time where the rate of cluster formation is so high it temporarily outpaces the rate of destruction. We are seeing the glorious, crowded peak of construction before the inevitable decay sets in. The other, more profound idea is that we are watching the very process that builds a galaxy's stellar backbone. Perhaps the vast majority of these clusters do indeed dissolve, their member stars scattering to form the diffuse, general population of stars that make up the main body of the future elliptical galaxy. Each brilliant cluster we see today could be a temporary nursery whose ultimate purpose is to seed the galaxy with stars, its magnificent structure sacrificed to build the larger whole. Are we witnessing the brief, glorious life of stellar metropolises, or the birth of an entire galactic field, one dissolving cluster at a time? The furious stellar nurseries of the Antennae may be hiding the ultimate cosmic bombs. Scattered among the brilliant superstar clusters are potential progenitors for gamma-ray bursts, the single most powerful explosions known to exist in the entire universe. These are not mere supernova which can outshine a galaxy. A gamma-ray burst, or GRB, is that same energy focused into two narrow, opposing beams of pure, high-energy radiation, concentrated into a blast that can release more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. To create such an apocalyptic event requires a very specific and very rare kind of star. The star must be extremely massive, and it must be rotating at an incredible speed. When such a star reaches the end of its brief life and collapses, its rapid spin helps to funnel the energy of the collapse into those two devastating jets. If one of these jets were pointed directly at Earth from even a distant galaxy, the effects could be catastrophic for our planet's atmosphere. The dense, chaotic environment of the Antennae Galaxies is a perfect factory for creating just these kinds of stellar monsters. The superstar clusters here are so packed with young, massive stars that gravitational interactions are constant, spinning stars up to tremendous velocities like a cosmic whirlpool. Furthermore, the frequent mergers of massive stars within these tight quarters could create the exact rapid rotators needed. This makes the Antennae a prime hunting ground for astronomers. They are not waiting to see a burst itself, which is a fleeting and random event. Instead, they are meticulously cataloging the population of massive, rapidly rotating stars, identifying the ticking time bombs that have the potential to one day unleash a flash of energy so brilliant it could be seen clear across the observable universe. What would it mean to witness such a titanic detonation from the relative safety of a million light-years away? The raw fuel for all this stellar violence is not spread evenly across the wreckage. Vast oceans of neutral hydrogen gas, the primary ingredient for building new stars, pool in strange and lopsided formations. Instead of a smooth, symmetric distribution, the gas has been flung into chaotic concentrations, heavily favoring the overlapping central region and streaming far out along the great tidal tails. Even more intriguing, one of the original galaxies appears to have held onto its gaseous reserves far more tenaciously than the other. This is not a balanced merger of equals in every respect, but a lopsided cosmic consumption. This profound asymmetry is a direct fossil of the initial collision, a clue written in invisible gas to the angle and speed of that first encounter millions of years ago. The galaxy that plunged in more directly or from a particular trajectory would have felt a different gravitational shock, potentially stripping it of a greater share of its star-forming material. This uneven distribution of fuel has a dramatic and visible consequence. It dictates the very map of stellar birth. The regions richest in gas, like the chaotic overlap zone, become the sites of the most ferocious starbursts, while gas-poor areas see far less activity. This means the future of the entire merger is being shaped by this initial, uneven hand of cards. The ultimate structure of the new elliptical galaxy, the final distribution of its stars, will be a direct result of where the gas was concentrated during this violent, formative era. We are watching a single, real-time experiment in galactic fluid dynamics, a billion-year lesson in how gravity stirs the cosmic pot. Beyond the thunder of supernova, a gentler crackle of stellar fireworks illuminates the darkness. These are nova, a different kind of cosmic explosion that plays out not in a star's core, but on its surface. They begin with a stellar partnership, a binary system where a white dwarf, the dense, Earth-sized core of a dead star, orbits a living companion. The white dwarf's gravity is so intense it can slowly steal hydrogen gas from its partner, pulling the material into a thin, hot layer on its own surface. Over time, the pressure and heat at the base of this stolen layer build to a critical point until the entire blanket of hydrogen ignites in a runaway thermonuclear explosion. It is a stellar flare-up, a brilliant flash that can make the star temporarily thousands of times brighter. Unlike a supernova which destroys its star, a nova is a surface event. The white dwarf survives, often to begin the slow process of stealing fuel all over again, setting the stage for another eruption in the future. Within the crowded stellar neighborhoods of the Antennae Galaxies, such binary systems are everywhere. The high density of stars dramatically increases the chances of these stellar thefts and subsequent explosions. So while a supernova is a final, dramatic death cry, a nova is a recurring fever, a constant, flickering background of lesser lights that adds its own layer of brilliance to the ongoing cosmic spectacle. This relentless cycle of theft and explosion seeds the surrounding space with new chemical elements, contributing to the complex soup from which future generations of stars and planets will form. This relentless cycle of creation and destruction has its own governing force, a phenomenon known as stellar feedback. It is the cosmic conversation between newborn stars and the raw material that birthed them. The most massive stars are not just brilliant beacons, they are powerful engines. They flood their surroundings with intense ultraviolet radiation and cast off their own outer layers in howling gales, stellar winds that move at millions of miles per hour. This energy and momentum pour into the surrounding clouds of gas, pushing and heating the material. In the Antennae Galaxies, this process is amplified to an extreme. Imagine a bubble rising in a pot of boiling water, but this bubble is sculpted by a star's fury. Stellar winds and the shockwaves from supernova act like cosmic blowtorches, carving out vast cavities in the nebulae. These are not small pockets, but gigantic voids that can span hundreds of light years, clearing entire regions of the very gas needed to form new stars. In this way, stellar feedback actively suppresses star formation, halting the process in its tracks by dispersing the stellar nursery. Yet, this is only half the story. The same force that suppresses can also trigger. As those immense bubbles expand, their outer edges sweep up the surrounding gas, compressing it into a dense, cold shell. Like a snowplow piling up a massive bank of snow, this shell can become so thick and heavy that it reaches its own gravitational tipping point. Fragments within the shell collapse and a new wave of star formation ignites, not randomly within the cloud, but in a brilliant ring tracing the outline of the original bubble. So the death of one generation of stars directly creates the nursery for the next. This is a self-regulating cycle, a furious loop of action and reaction. The system is both destroying its own fuel and using that destruction to build anew. It is a delicate balance between chaos and order, all orchestrated by the stars themselves. How does this incredible feedback loop ultimately determine the final size and shape of the newborn galaxy? A faint, pervasive glow settles over the wreckage, a luminous fog that clings to the spaces between the stars. This is diffuse ionized gas, a superheated plasma so thin it will be considered a near-perfect vacuum in any laboratory on Earth. It is the ghostly atmosphere of the entire collision, energized by the brilliance of its youngest and most massive stars. Their intense ultraviolet radiation acts like a cosmic blowtorch, striking neutral hydrogen atoms and violently stripping away their electrons, a process we call ionization. This leaves behind a sea of charged particles, protons and electrons, all swirling in a hot, tenuous mist that emits its own soft, characteristic light. The temperature of this gas is staggering, reaching tens of thousands of degrees, yet its incredible thinness means you could fly a spaceship through it and barely feel the heat. Its very presence is a direct measure of the ferocious energy pouring out of the starburst. By mapping the distribution and temperature of this glowing haze, astronomers can perform a kind of cosmic accounting. They can tally up the total energy output from all the massive stars, even those hidden deep within dusty cocoons, and track how that energy propagates through the galactic environment. This faint glow is the final, dissipated breath of stellar fury, a signature of the immense power that both builds and erodes the structure of the merging galaxies. How far does this energized fog extend, and what does its ultimate escape into intergalactic space mean for the future of this cosmic system? Amidst the galactic chaos, the fate of entire solar systems hangs in the balance. While stars themselves almost never physically collide in this vastness, the gravitational stability that allows planets to orbit peacefully is shattered. Imagine a star and its family of planets sailing smoothly through space, their orbits as predictable as clockwork. Now picture another star or even a dense cluster of stars passing nearby. The sudden, immense gravitational pull from this intruder acts like a cosmic hand, giving a violent and unpredictable tug on the entire system. The delicate gravitational dance that has persisted for billions of years is thrown into disarray. A gas giant like Jupiter could be ripped from its orbit, flung out of the solar system entirely to become a rogue planet, a dark and frozen wanderer in the interstellar void. An Earth-like world in the habitable zone could be knocked inward, sent on a death spiral into its own sun, or outward, into a deep freeze that would lock its oceans in perpetual ice. For any life that may have evolved on such a world, this would be an apocalypse on a scale beyond comprehension. The sky would change in an instant, the familiar constellations replaced by a brilliant, terrifying chaos of alien suns. The very ground would tremble from gravitational tides, and the climate would be torn between scorching heat and absolute zero. The Antennae Galaxies are likely creating countless such planetary refugees and casualties right now, scattering frozen or burning worlds as collateral damage in a war between galaxies. What would it be like to witness the end of your world, not from within, but from the heavens themselves? Even after a supernova's brilliant flash fades from view, its story is not over. The initial burst of light races outward at the ultimate speed, illuminating everything in its path for a few brief weeks. But in a dusty environment like the Antennae Galaxies, that light does not simply vanish into the void. It slams into vast, dark clouds of cosmic dust, the same material that once served as stellar nurseries. These dust grains do not absorb the light, they act like countless microscopic mirrors, reflecting it, scattering it, and sending it off in new directions. Because this reflected light takes a longer, indirect path to reach our telescopes, it arrives much later than the light that came straight to us from the explosion. The result is a ghostly, expanding shell of light that appears to move faster than light itself. This is a light echo, a cosmic illusion of motion born from simple geometry and the finite speed of light. We see the flash of the supernova, and then, years or even decades later, a faint ring-like glow emerges around the location of the long-dead star. This ring is not a physical object, it is the reflection of that ancient explosion, still traveling through space and gradually illuminating more distant dust clouds. It is a delayed broadcast of a cataclysm that happened long ago. In the Antennae, with its supernova-rich environment and abundant dust, these echoes are like ripples in a pond, each one a time capsule allowing us to study the same supernova explosion multiple times from different angles and at different moments in its fading life. What other secrets of these stellar deaths are still traveling toward us, hidden in the echoes of light? Far beyond the graceful arcs of starlight, the collision reveals a hidden dimension of its power. Our most sensitive radio telescopes capture a faint, sprawling glow enveloping the entire system, immense lobes of energy that dwarf even the long tidal tails. This is synchrotron radiation, a ghostly signature of violence. It is created when electrons, accelerated to nearly the speed of light, spiral wildly along magnetic field lines. Each twist in that invisible cosmic web forces these particles to shed a tiny amount of energy, releasing the radio waves we detect. It is the same basic process that lights up a hospital MRI machine, but here it is magnified to an incomprehensible scale. These electrons do not reach such incredible speeds on their own. They are catapulted by the most powerful engines in the merger. The shock waves from countless supernovae act as natural particle accelerators, a relentless cosmic slingshot that hurls electrons into the void. But there may be an even more potent source. The supermassive black holes at the galaxy's hearts, as they feast on surrounding matter, can blast out colossal jets of plasma. These jets could be pumping a steady stream of high-energy particles directly into the lobes, inflating them like vast, invisible balloons. This radio glow is therefore a map of the system's true energy budget, a portrait of the immense, invisible forces that surround the visible wreckage. It shows us that the drama of the antennae is not confined to the stars and gas we can see, but extends far into the darkness, a halo of pure power born from the collision's fury. Deep within the hearts of the most colossal superstar clusters, a new kind of gravitational monster may be taking shape. These are not the stellar mass black holes left by single stars, nor are they the supermassive giants at the galactic core. They are the missing links, the intermediate mass black holes, with the weight of hundreds or even thousands of suns crushed into a single point. The Antennae Galaxies, with its abundance of incredibly dense and massive stellar clusters, is the perfect cosmic laboratory to search for them. How could such an object form? One compelling theory is that in the frantic density of a young superstar cluster, stellar mass black holes can sink to the center through gravitational interactions like heavy stones settling in a pond. Once there, they can merge with one another or voraciously consume the surrounding stars and gas, growing steadily larger over time. This process, known as runaway core collapse, could forge a single, intermediate mass black hole right in the cluster's heart. Finding one would be a monumental discovery, as it would provide the clearest evidence yet for how the supermassive black holes at the centers of galaxies themselves might have first gotten their start by growing from these very seeds. The hunt is on, with astronomers meticulously studying the motions of stars at the very centers of the antennae's brightest clusters. looking for the telltale, frantic whirling that would betray the presence of an invisible, massive anchor. Each cluster is a potential hiding place for this cosmic missing link, a dark heart beating within a city of stars. This constant storm of supernova and stellar winds is doing far more than just shaping the galaxy. It is fundamentally changing its chemical identity. With every massive star that explodes, it acts as a titanic forge, blasting newly created elements out into the void. The interstellar medium, the raw gas between the stars, is no longer the pristine hydrogen and helium left over from the Big Bang. It is now being systematically polluted with heavier atoms. Oxygen, carbon, silicon, and iron are all being forged in stellar cores and then scattered by these violent deaths. Stellar winds contribute as well, continuously blowing enriched material off the surfaces of giant stars, like a constant, slow drizzle of metallic rain into the cosmic environment. This process is known as chemical enrichment, and here it is happening on an industrial, galactic scale. The entire system is gradually becoming more metal-rich, a term astronomers use for any element heavier than helium. This has a profound implication for the future. When the next generation of stars begins to form from this enriched gas, they will be born from a different recipe. They will naturally contain a higher abundance of these heavy elements, and with those stars will come new planets. Planets forming from this metal-rich dust will have a much greater supply of the raw ingredients needed for rock and metal worlds. A future Earth-like planet born here would have more iron for its core, more silicon for its mantle, and more carbon and oxygen for its oceans and atmosphere. The very chemistry that led to life in our own solar system would be supercharged in such an environment. This ongoing enrichment cycle means the potential for habitability in the future Antennae Galaxy could be far greater than it was in its primordial past. The violence of today is literally seeding the galaxy with the building blocks for more complex and potentially life-friendly worlds tomorrow. This invisible rain of atomic shrapnel is a relentless and unseen force within the collision. We call them cosmic rays, but they are not rays of light. They are the bare nuclei of atoms, protons, and heavier elements like carbon and iron that have been torn from their electrons and accelerated to almost the speed of light. Their source is the very violence we have been witnessing. The colossal shock waves from supernova, expanding through space at millions of miles per hour, act as the universe's most powerful natural accelerators. A drifting atomic nucleus can get caught in the magnetic fields carried by these shock waves, bouncing back and forth across the expanding wall of energy like a ping-pong ball in a hurricane. With each crossing, it gains a tremendous burst of speed until it is finally flung out into the galaxy, a single hyper-energetic bullet. The Antennae Galaxies, with its constant thunder of stellar explosions, is a veritable factory for these particles, saturating the entire system with an invisible high-energy fog. So what happens when this fog drifts into one of the vast, dark molecular clouds, the same clouds that are the cradles for new stars? The cosmic rays pierce deep into these cold, dark regions, their immense energy stripping electrons from the atoms and molecules they encounter. This ionization drives a hidden, complex chemistry, sparking reactions that would never occur in the cold, quiet dark. They help forge more complex molecules, the very precursors to the organic compounds that are the building blocks of life. This energetic fog does not just create chemistry, it also creates light. When these relativistic particles slam into the nuclei of slower-moving atoms in the gas or into photons of starlight, the collisions are so violent they can generate gamma rays, the most energetic form of light in the universe. This creates a faint, diffuse gamma-ray glow that hangs over the entire merger, a final, high-energy signature of the incredible particle acceleration happening within. The drama of the antennae is not just in what we see, but in this invisible, energetic rain that etches its story into the chemistry of future worlds. The combined mass of the Antennae Galaxies could be bending the very fabric of space around them. This incredible distortion is known as gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. The principle is deceptively simple. Any object with mass warps the space-time around it like a heavy ball placed on a stretched rubber sheet. Light from a distant object traveling in a straight line through this warped space will have its path curved. The Antennae system, with a combined weight of hundreds of billions of stars, vast clouds of dark matter, and all the turbulent gas, creates a particularly significant warp. If a far more distant galaxy lies in a perfect line directly behind this cosmic wreck, from our viewpoint, its light must pass through this warped region on its way to our telescopes. The result is not a clear image but a natural cosmic telescope. The gravity of the antennae acts as a lens, magnifying and distorting that background galaxy's light. It might stretch the galaxy's image into a faint, luminous arc, or even split it into multiple, identical copies arranged in a perfect ring, known as an Einstein ring. The chance alignment for such a perfect effect is incredibly rare, but even a partial lensing event would be a monumental discovery. It would grant us a magnified view of a galaxy from the early universe, an object otherwise far too faint and small to study in any detail. This natural telescope allows astronomers to peer deeper into the cosmos than our own instruments ever could, using the chaos of a nearby collision to illuminate the ancient past. What ancient secrets might be hidden, magnified in the light that filters through this cosmic wreckage? At the chaotic heart of the collision, where the two galactic disks grind directly through one another, lies the overlap region. This is the epicenter of the firestorm, a zone of unimaginable density where entire spiral arms from different galaxies are being forced together. The gas clouds here are not merely drifting past each other, they are colliding head-on like two weather fronts crashing to create a perfect storm of creation. The sheer compression is beyond anything found in a normal galaxy. Vast nebulae, each 1 light-years across, are slammed together with such force that they collapse not in isolated pockets, but in a near-continuous rolling wave of implosion. This area glows with a ferocious intensity, blazing in the infrared from the heat of buried young stars, in the visible spectrum from their brilliant blue light, and in the radio from the excited molecules within the shattered clouds. It is a stellar nursery operating at its absolute extreme, one of the most prolific and violent star-forming factories in our entire cosmic neighborhood. Here, the very process of star birth is accelerated and amplified, creating stars at a rate that defies belief and crams them into a space of terrifying density. What would it be like to witness the dawn of 1,000,000 suns, all igniting within the same celestial forge? Many of those brilliant points of light are not single stars at all. They are cosmic pairs or even triplets locked in a tight gravitational dance. These are binary and multiple star systems, and within the antennae, their fate is anything but certain. In a calm galaxy, such stellar partnerships often form together from the same cloud, living out their lives in a stable orbit. But here, the chaotic environment throws everything into question. The crowded stellar neighborhoods mean close encounters are the rule, not the exception. When two single stars pass near each other, the complex gravitational pull between them can sometimes rob them of their independence. Instead of flying apart, they become gravitationally bound, captured into a new, often unstable binary system. This is a forced partnership, a celestial marriage born from the turmoil of the crowd. These newly forged pairs are critically important, for they are the seeds of future cosmic fireworks. A binary system where one star is a dense white dwarf sets the stage for the recurring explosions of nova. If one of the partners is a neutron star or a black hole, it can pull material from its companion, heating it to millions of degrees and creating a brilliant, flickering X-ray binary, like the ultraluminous sources we see scattered throughout the wreckage. And the ultimate fate for some of these pairs is even more profound. Two neutron stars, the super-dense cores left after supernova, can spiral inward for billions of years, their orbits decaying until they finally collide. That merger is one of the universe's most powerful events, shaking the very fabric of space-time and sending out ripples known as gravitational waves. The Antennae Galaxies, in its frantic state, is likely forging countless such future messengers, creating the very systems that will one day announce their final, violent union across the cosmos. This interstellar gas and dust, the very fuel for all the stellar fire, cannot last forever. Its ultimate fate is being sealed by the very forces it unleashed. A significant portion of this raw material is being consumed in the relentless firestorm of star formation, locked away for billions of years within the new suns. But another, perhaps larger, fraction is meeting a far more dramatic end. The combined fury of supernova explosions and the relentless pressure of stellar winds from massive stars is generating immense galactic winds. These are not gentle breezes, but titanic outflows of superheated gas moving at thousands of kilometers per second. Think of a hurricane, but one that scours an entire galaxy. This ferocious energy punches right through the gravitational grip of the merging galaxies, lifting colossal streams of enriched gas and dust and hurling them out into the vast, empty spaces between galaxies. This process is a crucial cosmic regulator. By ejecting its own star-forming fuel, the system slams the brakes on its own growth, preventing the formation of an even more monstrously large galaxy. The expelled material does not simply vanish. It becomes part of the intergalactic medium, the thin, invisible soup that fills the voids between galaxy clusters. This ejected gas is rich with the heavy elements forged in stellar cores and supernova, polluting the primordial hydrogen of deep space with the seeds of future complexity. The very elements that might one day form planets around a star in a distant, unborn galaxy are now being scattered by this ancient collision. The Antennae Galaxies are not just building a new island universe, they are fertilizing the entire cosmic landscape with the ashes of their own brilliant, self-destructive fire. The very stars themselves have lost their way. In a normal spiral galaxy like our own, stellar motion is a grand, orderly ballet, with stars tracing graceful, predictable orbits around the galactic center. But here, in the heart of the collision, that cosmic dance has descended into a chaotic free-for-all. The gravitational disturbance from the merger has shattered the old rhythms, sending stars on wild, random trajectories that crisscross and loop in a state of gravitational anarchy. To map this pandemonium, astronomers turn to a powerful tool called spectroscopy. They do not just take a picture, they dissect the light from individual stars, looking for the subtle shifts in color that betray motion. A star moving toward us has its light squeezed, shifting it toward the blue end of the spectrum. A star moving away has its light stretched, shifting it toward red. By measuring these Doppler shifts for thousands of stars across the wreckage, they can chart the complex, turbulent flow of stellar traffic. This velocity map is far more than a record of chaos. It is a key to the invisible. The gravitational pull required to orchestrate this specific pattern of stellar motion, however disorganized, must come from somewhere. By subtracting the pull from all the visible matter, the stars and gas we can see, astronomers are left with the gravitational signature of the true master of the dance, the dark matter halo. The peculiar, chaotic kinematics of the stars are therefore a direct window into the shape and strength of this invisible scaffold, the hidden architecture that is ultimately holding the entire cosmic wreck together. How does this invisible hand guide the final form of the new galaxy taking shape from the ruins? Even the most massive stars are not safe from being cast out into the void. Within the dense heart of a superstar cluster, a gravitational game of billiards is constantly underway. Stars are perpetually nudging and pulling at each other as they orbit the cluster's center. When two stars swing particularly close, their gravitational interaction can become a slingshot. One star, often the lighter one, gets a tremendous kick of velocity, accelerating so rapidly that it can achieve escape velocity. It breaks free from the cluster's gravitational hold entirely, becoming a runaway star. These are not small, dim suns being exiled. Some of the fastest and most famous runaways are brilliant blue supergiants, stellar titans many times heavier than our own sun, now racing across the galaxy at speeds of hundreds of thousands of miles per hour. As these stellar fugitives tear through the quieter regions of the interstellar medium, they create a spectacle of their own. The space between stars is not a perfect vacuum. It contains wispy clouds of gas and dust. The runaway star, moving faster than the speed of sound in that gas, plows into it like a speedboat through water. It pushes a wall of material ahead of itself, compressing and heating the gas until it glows with a faint, ethereal light. This forms a beautiful, arcing structure called a bow shock, a luminous crescent that always points away from the direction of the star's frantic travel. It is a cosmic wake, a visible scar left by the star's violent expulsion. Some of these runaways are given such a powerful kick that they do not just leave their cluster, they leave the galaxy itself. They are flung beyond the gravitational pull of the entire merging system, destined to spend eternity as lone giants in the profound, empty darkness of intergalactic space. What would the night sky look like from a planet orbiting such a solitary, exiled sun, with no other stars to keep it company in the endless black? All this violence and creation is mostly hidden from our eyes. The true scale of the Antennae's power is not in the brilliant blue stars we can see, but in the dull, warm glow our eyes can never perceive. This system is classified as a luminous infrared galaxy, a LIRG for short. That name sounds technical, but the idea is simple. The vast majority of the light produced by the Antennae Galaxies is not the visible light from its stars. It is infrared radiation, a form of heat. The source of all that heat is the cosmic dust, the fine, dark grains of carbon and silicon scattered everywhere by supernova. This dust acts like a thick blanket, absorbing the intense ultraviolet and visible light from the millions of newborn stars. It heats up just like asphalt on a hot summer day, and then re-radiates that captured energy as a powerful, diffuse infrared glow. The numbers involved are staggering. The total energy the antennae emits in the infrared alone is many times greater than all the energy our entire Milky Way galaxy emits across all wavelengths combined. This incredible output places it in a special category of cosmic objects, a class that includes some of the most energetic and dust-shrouded galaxies in the universe. This classification is not just a label, it is a key that connects this nearby collision to the most violent and formative events in cosmic history. In the early universe, when galaxies were closer together and collisions were far more common, luminous infrared galaxies were the dominant powerhouses. The Antennae gives us a nearby, detailed look at the same kind of engine that drove galaxy growth and star formation billions of years ago. By studying its infrared signature, we are essentially looking back in time, understanding how these colossal mergers shaped the universe we see today. What other secrets of our cosmic past are locked within this warm, invisible glow? This cosmic wreck refuses to sit still for a single photograph. The Antennae Galaxies are a prime target for time-domain astronomy, a field dedicated to watching the sky change in real time. Unlike static images of most celestial objects, this collision offers a dynamic front-row seat to evolution. A new supernova can suddenly flare into existence, a brilliant new point of light where none existed the night before. Variable stars pulse and throb, their brightness waxing and waning over days or weeks as they swell and contract. Even the vast structure of the gas clouds themselves is in constant motion, sculpted by stellar winds and shockwaves that reshape the nebulae over months and years. Continuous monitoring with powerful telescopes transforms our view from a single snapshot into a cosmic movie, a time lapse of galactic transformation. Each new observation adds another frame, revealing how shockwaves propagate, how star-forming regions ignite and then fade, and how the tidal tails slowly stretch and dissolve. This is not just about watching for dramatic explosions. It is about tracking the subtle, relentless flow of change that defines the life of a galaxy. What would it be like to watch 1,000,000 years of cosmic evolution compressed into a single human lifetime? Deep within the galactic cores, a more subtle form of power is awakening. The supermassive black holes at the hearts of the original galaxies are no longer dormant. As vast rivers of gas and dust are funneled toward them by the merger's chaos, these gravitational monsters have begun to feed. We classify this phase as active galactic nuclei, or a GN, a state where the central black hole is actively consuming material. The antennae GN are not the brilliant, universe-spanning quasars seen in some distant galaxies, but their influence is nonetheless profound. Imagine a buried engine humming with power deep underground. As matter spirals into the black hole's accretion disk, it heats to millions of degrees, glowing fiercely across the electromagnetic spectrum. This intense radiation pushes outward, exerting pressure on the surrounding gas. In some cases, the black hole's immense magnetic fields can also funnel some of the infalling material into tight, narrow beams that blast outward at nearly the speed of light. These are relativistic jets, cosmic blowtorches that can carve through the interstellar medium for thousands of light years. While their jets may not be visible on a galactic scale yet, the combined radiation and potential outflow from both black holes adds a significant new layer of energy to the system. It is another source of heat, another source of pressure, stirring the already turbulent pot of star formation and gas dynamics. This GN activity is a quiet but growing counterpoint to the stellar fireworks, a deep, resonant note in the symphony of the collision that could ultimately help regulate how many new stars the galaxy can form. How will this buried engine shape the final structure of the new galaxy beginning to coalesce from the wreckage? Scattered throughout the chaos are the silent graves of former giants. Every brilliant supernova and every nova flare leaves behind a dense, compact corpse, and the Antennae Galaxies have become a sprawling cemetery for these stellar remnants. 3 primary types of graves mark this cosmic graveyard. The first are white dwarfs, the exposed, Earth-sized cores of stars like our own Sun, slowly cooling into blackened cinders over billions of years. The second are neutron stars, the unimaginably dense balls of matter forged when a more massive star collapses, squeezing more than the mass of our entire Sun into a city-sized sphere. And the third are the stellar mass black holes, the darkest graves of all, where gravity is so strong that not even light can escape. While these objects are incredibly difficult to spot individually amidst the stellar firestorm, their collective presence is immense. They add a tremendous, unseen mass to the system, a hidden gravitational anchor woven through the wreckage, but some of these corpses refuse to rest in silence. When one of these remnants, particularly a neutron star or a black hole, orbits a living companion star, it can begin to feed. Its immense gravity pulls a stream of gas from its partner, forming a superheated disk of material spiraling inward. This accretion disk glows with an intense, flickering X-ray light, revealing the hidden corpse as a brilliant X-ray binary. These beacons are the tombstones that speak, the only way we can directly detect the vast population of the dead that now outnumbers the living giants in this ancient collision. These shock waves do more than just trigger new stars, they superheat the very substance of space itself. When 2 colossal gas clouds slam into each other at supersonic speeds, or when the blast wave from a supernova plows into the surrounding medium, the collision is not a gentle merging. It is a cosmic traffic jam of unimaginable violence. The gas particles are suddenly and brutally compressed and accelerated, their collective motion transformed into intense, chaotic heat. This process, known as shock heating, can raise the temperature of the gas to staggering millions of degrees. At such extreme temperatures, the gas becomes a seething plasma, a state of matter where atoms are torn apart into a soup of free-flying atomic nuclei and electrons. And this plasma does not glow with the familiar colors of a nebula. It emits a far more energetic light, shining brilliantly in the high-energy X-ray portion of the spectrum, completely invisible to our eyes. To X-ray telescopes like Chandra, however, the Antennae Galaxies are transformed. They are no longer just a tapestry of stars and dust, but a landscape of colossal glowing cavities. These are the bubbles and filaments of shock-heated gas, vast structures that trace the outlines of the most energetic events in the merger. Each one is a real-time map of energy transfer, showing us where the raw kinetic violence of the collision is being converted into pure, radiant heat. These X-ray cavities are the lingering thermal scars of the merger's fury, a permanent record of the shock waves that continue to ripple through the galactic wreckage. Pinpointing the exact location of this cosmic wreck is a scientific puzzle with profound implications. The Antennae Galaxies do not come with a convenient signpost announcing their distance. For astronomers, measuring how far away they truly are is a critical and surprisingly difficult task. The best estimates place them somewhere between 45 and 65 million light-years from Earth, a range so vast it spans millions of light-years of uncertainty. This might seem like a minor detail, but in cosmology, distance is everything. It is the fundamental ruler we use to measure the true nature of the universe. If we get the distance wrong, we get almost everything else wrong too. The incredible luminosity we observe, the brilliant glow of its superstar clusters, and the ferocious output of its starburst all depend on an accurate distance measurement. A galaxy that is actually closer than we think would be intrinsically dimmer, its stellar fireworks less powerful. A galaxy that is farther away must be inherently brighter and more energetic to appear as brilliant as it does to our telescopes. This uncertainty directly affects our understanding of the true scale of the phenomena within it. Are the superstar clusters truly as massive as we calculate, or are they smaller, just appearing large because they are nearer? Is the rate of star formation truly hundreds of times that of the Milky Way, or is it a less extreme, though still impressive, figure? The slight variations in distance, a difference of 20 million light-years, ripple through every calculation. They change our perception of the antennae's true power, making it one of the most brilliant and important, yet paradoxically elusive, collisions in our cosmic neighborhood. How can we ever hope to understand the grandest scales of the universe if we cannot even be sure of the distance to one of its most spectacular nearby events? A deep, rhythmic hum underlies all this visible chaos. Long after the brilliant light of the collision has faded, the Antennae Galaxies will continue to broadcast its story, not with light, but by shaking the very fabric of the universe. The countless binary systems forged in this stellar maelstrom, the pairs of neutron stars and stellar mass black holes, are the key. These dense stellar corpses are locked in a tightening gravitational embrace, their orbits decaying over millions of years as they radiate energy away in the form of ripples in spacetime. These ripples are gravitational waves, the same kind of cosmic vibrations first detected by LIGO in 2015. When the orbits of these pairs finally decay completely, the two objects spiral inward at a significant fraction of the speed of light and collide in a final, violent merger. That catastrophic impact sends a powerful, fleeting burst of gravitational waves racing outward at the speed of light. The antennae, with its prodigious output of such binary systems, is likely a significant contributor to what scientists call the stochastic gravitational wave background. Imagine the sound of a massive stadium crowd. You cannot pick out any single voice, but you hear the collective roar as a constant, pervasive hum. The antennae's countless mergers, added to those from all the other galaxy collisions across the cosmos, create a similar background hum of spacetime itself. Our current detectors cannot yet isolate a single merger from the antennae from this universal chorus. The signal is too faint, the distance too great. But each new generation of gravitational wave observatories, both on Earth and in space, brings us closer to tuning into this specific channel. One day, we may be able to listen directly to the low, persistent rumble of this cosmic wreck, a vibration that began millions of years ago and is only now reaching our instruments, telling a story of ancient violence written not in light but in the bending of reality. The collision paints its portrait in vivid, contrasting colors of stellar life and death. Scattered across the wreckage are brilliant knots of sapphire light, immense stellar metropolises glowing with the fierce intensity of youth. These are the blue blob populations, vast assemblies of the hottest and most massive stars in the universe. Each one is an O-type or B-type star, a true stellar titan that burns with a ferocious blue-white fire. Their brilliance is so extreme that a single one can outshine our sun by 1,000,000 times, and here they are gathered in their thousands. This collective blue light is what gives the active star-forming regions their unmistakable hue, a sharp, piercing azure that cuts through the cosmic gloom. This color is not just for show, it is a direct indicator of cosmic temperature and age. These stars are so immensely hot that they emit most of their energy in the blue and ultraviolet parts of the spectrum, a visual declaration of their raw power. They stand in stark opposition to the duller, redder glow that pervades the quieter parts of the system. That crimson light comes from two sources: the vast populations of ancient, cooler stars that formed long before the collision, and the warm, diffuse emission from all the cosmic dust heated by this stellar fury. The entire optical view of the antennae is a battle between these colors, a celestial canvas where the brilliant blue of new birth fights for dominance against the deep red of old age and dusty death. These blue blobs are the visible heartbeat of the starburst, but their glory is tragically fleeting. A star like our sun can shine steadily for 10 billion years, but these brilliant blue giants have no such luxury. They consume their nuclear fuel at a reckless pace, destined to explode as supernova after only a few million years. Their very prevalence is proof of an ongoing, violent firestorm of star formation. We are not seeing a constant, gentle background of blue stars. We are witnessing a spectacular but temporary peak of stellar birth, a wave of brilliant blue light that will, in a cosmic instant, fade away. What happens to the color of a galaxy when an entire generation of its brightest stars suddenly vanishes? Far beyond the heat of the infrared and the glare of visible starlight, a deeper chill holds the final secret to this collision's future. Our most powerful radio telescopes, tuned to the faint whisper of submillimeter waves, have peeled back the brilliant outer layers of the antennae to reveal its cold, dark skeleton. This is the domain of the truly frigid, where temperatures hover just a few tens of degrees above absolute zero. At these wavelengths, the dazzling blue star clusters and the glowing red giants simply fade into the background, and an entirely new structure emerges from the darkness. What appears in optical images as relatively empty space between the bright knots of starlight is in fact packed with an immense, hidden reservoir of cold molecular gas and dust. This is the true, untouched fuel for star formation, the raw hydrogen and other molecules that have not yet been swept up by the firestorm. It is a cosmic stockpile of staggering proportions, a deep freeze of potential that outlines the true mass and shape of the merging system in a way visible light never could. This cold material is the ultimate inventory for astronomers, a direct measure of how many more stars this galaxy can build. By mapping its distribution, we can see not just where stars are forming now, but where they will form millions of years from now. The chaotic overlap region, already brilliant with newborn stars, is also a colossal concentration of this cold gas, promising that the firestorm there is far from over. Even the long, graceful tidal tails, which seem to be streams of exiled suns, are revealed to be rich with these frigid molecular rivers, potential sites for star formation far from the chaotic core. This cold, dark map is the true blueprint of the Antennae's destiny, showing that the violence of today is built upon a foundation of profound cold, and that the future of this cosmic wreck is still being written in the silent, frozen dark. This storm of colliding gas is not a smooth and orderly flow. The interstellar medium itself is caught in a state of profound turbulence, a chaotic churn that resembles a hurricane spanning thousands of light years. Vast clouds do not simply drift, they are whipped into a frenzied, supersonic froth. The primary drivers of this chaos are the very forces we have already witnessed. Each supernova explosion acts like a titanic depth charge, sending immense shockwaves rippling through the surrounding gas. At the same time, the complex gravitational tides from the merging galaxies constantly stretch and shear the material, injecting energy into the system like a giant, invisible hand stirring a cosmic pot. This turbulence creates a delicate and paradoxical balance. On one hand, the violent, random motions within a gas cloud generate a kind of internal pressure, like the chaotic buzzing of bees in a swarm. This pressure can actually support the cloud against its own gravity, holding it up and preventing a wholesale collapse. It keeps the vast reservoirs of gas puffed up and stable. Yet within that same maelstrom, turbulence also creates the seeds of its own destruction. As these supersonic currents collide and intertwine, they create regions of intense compression. Imagine the wake behind a speedboat with swirling eddies and regions where the water is forced together. In the same way, turbulent flows in space slam gas clouds into each other, forging incredibly dense knots and filaments within the larger cloud. In these localized pockets, the enhanced density overwhelms the supporting pressure of the turbulence. Gravity suddenly finds a decisive advantage, and these knots become the privileged sites for gravitational collapse. So, turbulence is both the guardian and the architect of star birth. It holds back the general collapse of a cloud while simultaneously forging the specific, dense cradles where new stars are destined to ignite. Without this pervasive chaos, the firestorm of creation in the Antennae might look very different. A slower, more placid process instead of the furious, brilliant explosion we see today. How does this invisible, churning energy ultimately dictate the final size and distribution of an entire generation of stars? The Antennae Galaxies are more than a spectacle, they are a cosmic proving ground. Supercomputers around the world run complex simulations, virtual universes governed by the laws of physics as we understand them. These digital models attempt to recreate the entire life cycle of a galactic collision, from first approach to final merger. But a simulation is only as good as its ability to mirror reality. This is where the Antennae provides the ultimate benchmark. It is our one detailed, near-by example of a major merger caught in its most active phase. Astronomers feed the known properties of the two original galaxies into their models, the mass, the gas content, the approach velocity. They then set the virtual clock running and wait to see if their digital creation can grow the long, graceful tidal tails we observe in the real universe. Can it reproduce the furious burst of star formation in the overlapping region, and at the correct, staggering rate? Does the final morphology, the overall shape and structure of the wreckage, match the telescope images? Very often, the first attempts fail. The simulated tails might be too short, or the starburst might ignite in the wrong place. Each mismatch is not a failure, but a clue. It tells the scientists that something is missing from their equations, perhaps the intricate role of magnetic fields, or the precise way stellar feedback regulates star formation. The Antennae acts as a strict teacher, pointing out the flaws in our theoretical homework. Every time a model is adjusted to finally replicate the Antennae's unique profile, our confidence in that model grows. We can then use it with greater assurance to peer back into the ancient universe, to understand the collisions that built the first giant galaxies. This real-world laboratory is quietly refining our entire understanding of how galaxies live, die, and are reborn throughout cosmic history. What other universal secrets are being unlocked by this single, chaotic wreck? That brilliant sapphire light blazing from the superstar clusters cannot last. Each of these stellar cities is a ticking clock, and the passage of time is written in the slow, inevitable shift of their color from a piercing blue to a deep, somber red. This transformation is known as the red sequence, a final, quiet chapter in the life of a star cluster. It begins with the most massive and brilliant stars, the same blue giants that define the cluster's youthful appearance. These titans burn through their nuclear fuel in a cosmic frenzy, living for only a few million years before meeting their explosive end. One by one, these brilliant blue lights flicker out in supernova blast. As they vanish, the collective color of the cluster begins to change. The next most massive stars follow, their lives only slightly longer, their own blue light fading away. This gradual dimming of the hottest stars is like a city slowly turning off its brightest neon signs, until only the warm, gentle glow of the streetlights remains. What is left behind are the smaller, less massive stars. These red dwarfs and aging red giants are the frugal citizens of the cluster, burning their hydrogen fuel so slowly that they can shine for trillions of years. Their light is cool and crimson, and as they become the dominant population, the entire cluster joins the red sequence, a vast graveyard of stars where the frantic energy of youth has been replaced by the steady, ancient glow of old age. The Antennae offers a unique snapshot of this entire life cycle. Scattered across its wreckage, we see clusters at every stage of this evolution. Some are still blazing with the pure blue fire of infancy. Others are in a transitional phase, their light whitened by a mix of blue and red stars, and some of the oldest clusters born in the earliest stages of the collision have already completed their journey, glowing with the quiet, red light of stellar retirement. This progression is the ultimate fate of every one of those magnificent superstar clusters. Their glorious blue phase is a fleeting moment, a brilliant but short-lived peak before they settle into a long, slow fade, becoming the ancient, red-globed clusters that will orbit the future elliptical galaxy for eons to come. Those microscopic flecks of dust are not just passive spectators in this collision. The extreme environment of the Antennae Galaxies acts as a colossal forge, likely creating dust grains unlike anything we find drifting in the calm of our own Milky Way. In a quiet galaxy, dust forms at a leisurely pace, condensing in the gentle outflows from aging stars. The resulting grains tend to be small and relatively uniform, like fine, well-sifted sand. But here, the rules are rewritten by violence. The intense radiation from countless young, massive stars bombards the dust, blasting away fragile outer layers and baking the grains into tougher, more resilient forms. Simultaneously, the relentless shockwaves from supernova act like cosmic tidal waves, slamming into dust clouds and smashing individual grains together at tremendous speeds. This is not a gentle merging, it is a high-velocity collision that can weld tiny particles into sprawling, fluffy aggregates like cosmic snowflakes forged in a furnace. These would not be the dense, compact specks we know, but complex, porous structures with vast surface areas. Their composition could be radically different, too. The sheer abundance of heavy elements blasted out by supernova might allow for grains rich in rare carbides or silicates that simply do not have the chance to form in quieter settings. How would this strange dust change the very appearance of the collision? These unusual grains would interact with light in fundamentally new ways. They might absorb and re-radiate starlight more efficiently, or scatter specific colors of light, subtly altering the hues we perceive in the tidal tails and nebulae. The entire infrared glow of the galaxy, that tremendous heat signature, could be shaped by the unique properties of this dust. We are likely looking at a cosmic laboratory for solid matter, a place where the very ingredients of future planets are being transformed into something new and alien under conditions of unimaginable stress. What kind of worlds could eventually form from such exotic, processed stardust? This galactic wind is a force of cosmic regulation, a self-imposed limit on the firestorm of creation. The combined fury of thousands of supernovae, each one a stellar detonation, does not simply fade into the void. Instead, it acts in concert, their shockwaves merging into a single, colossal outflow that scours the entire galaxy. Imagine a hurricane, but one born from exploding stars, with winds moving at thousands of kilometers per second. This is not a gentle breeze, it is a titanic gale that punches right through the gravitational pull of the galactic disk. It lifts colossal streams of superheated gas, a fog rich with newly forged heavy elements, and hurls it high above the starry plane, out into the halos of dark matter that surround the visible wreckage. Some of this ejected material is moving so fast it will never return. It escapes the galaxy's grip entirely, bleeding the system of the very fuel it needs to build new stars. This is the galaxy's method of slamming the brakes on its own growth, a violent act of self-sabotage that prevents it from becoming a monstrously large entity. Yet for some of the gas, the journey is not permanent. As this hot, metal-rich plasma climbs to its highest point in the galactic halo, it begins to cool. It condenses into denser, colder clouds that can no longer resist the pull of gravity. These clouds then rain back down onto the galactic disk, a cosmic fountain of returning material. This returning gas is not the same as before. It has been enriched by its journey, infused with the heavy elements from the supernova that launched it. It will eventually seed new rounds of star formation, but this time with a richer chemical recipe. This incredible cycle of wind and fountain is a delicate balance between loss and rebirth. It dictates how long the starburst can last and ultimately determines the final mass and chemical makeup of the new galaxy taking shape from the chaos. How much of this galactic breath will be a final exhalation, lost to the void forever, and how much will return to whisper the promise of new suns? Scattered among the blue supergiants is an even more extreme stellar population, the Wolf-Rayet stars. These are not merely massive stars, they are stellar monsters in their final death throes. Each one began its life with a weight dozens of times greater than our Sun, but it has already burned through its hydrogen fuel and is now furiously fusing heavier elements in its core. This frantic internal energy production creates a pressure so immense that it violently blows the star's own outer layers away into space. The result is a star literally tearing itself apart, shrouded in a continuous titanic gale of stellar wind. These winds move at millions of miles per hour, ejecting a sun's worth of mass into the cosmos every 100,000 years. This furious self-stripping exposes the star's brilliant, superheated core, which floods the surrounding ejected gas with intense ultraviolet radiation, causing it to glow with a strange and distinctive spectrum. To an astronomer's eye, this creates sharp, bright emission lines that act like a fingerprint, making these otherwise hidden stars suddenly visible across the vast distances of the collision. They are cosmic lighthouses signaling their own imminent demise. Their rarity makes each one a precious find, for a Wolf-Rayet star's entire lifespan is a fleeting cosmic blink, perhaps only a few 100,000 years from this dramatic phase to its final supernova. In that short time, they perform a crucial act of cosmic alchemy. The powerful winds are not just blowing off hydrogen, they are carrying away newly forged elements cooked in the star's interior, enriching the surrounding gas with carbon, nitrogen, and oxygen. The very elements essential for life are being scattered into the void by these dying giants, seeding the Antennae's future with the potential for planets and perhaps one day biology. What other violent transformations are required to build a universe capable of complexity? Even the spaces between the stars are alive with a faint, pervasive crackle of energy. This is the X-ray background of the antennae, a diffuse, hot glow that blankets the entire collision. It is not the sharp, brilliant pinpoint of an ultraluminous source, but a soft, all-encompassing haze. So where is this faint light coming from? astronomers face a compelling cosmic detective story with two primary suspects. The first possibility is that we are seeing the collective light of millions of unresolved faint sources. Imagine standing in a city at night, looking at a distant hill covered in lights. From a distance, the individual street lamps and house lights blur together into a single, diffuse glow. In the antennae, this could be the combined X-ray output of countless faint objects, like binary star systems where a white dwarf or neutron star is steadily siphoning material from a companion. Each one is too dim to see individually from our vast distance, but together, their accumulated emission creates the background haze we detect. The second suspect is truly diffuse hot gas. The entire system could be filled with a superheated plasma, a thin, seething soup of gas heated to millions of degrees by the relentless shockwaves from supernova and colliding gas clouds. This would be the lingering thermal breath of the merger's violence, a permanent atmosphere of pure heat. Unraveling which source dominates is not just an academic exercise, it is fundamental to understanding the thermal history of the entire collision. If the glow comes mostly from unresolved stars, it tells a story about the incredible population of stellar corpses and binary systems forged here. But if it is truly diffuse gas, it reveals how effectively the merger's fury can heat the interstellar medium to staggering temperatures, creating a permanent, high-energy fog that will slowly cool over eons. Each observation brings us closer to solving this puzzle, to understanding whether the spaces between the stars are filled with the quiet hum of countless hidden suns, or the fading warmth of a billion ancient explosions. This violent nearby crash is a perfect window into the universe's wild youth. The Antennae Galaxies offer us something incredibly rare, a close-up view of a process that was once the dominant force in shaping the cosmos. Billions of years ago, when the universe was much smaller and denser, galaxies were packed tightly together. Collisions like this one were not rare spectacles, they were commonplace events, the primary engines driving galactic growth. But those ancient mergers are now impossibly far away, their light stretched and faded by the expansion of the universe. Our most powerful telescopes see them only as faint, reddened smudges, their intricate details lost to cosmic distance and time. We are left with a fundamental question: what exactly are we looking at in those distant, blurry images? This is where the antennae becomes our most vital interpreter. It acts as a nearby analog, a Rosetta Stone for decoding the ancient universe. By studying this local collision in exquisite detail, by mapping its superstar clusters, its galactic winds, and its furious starbursts, we can learn to read the faint signatures hidden within those distant smudges. When we see a similar infrared glow or a particular radio signature from a galaxy 10 billion light-years away, we can now infer with greater confidence that we are witnessing a similar firestorm of creation, a similar self-destructive growth spurt. The antennae provides the crucial context, transforming those enigmatic blobs from abstract data, points into vivid stories of cosmic construction. It teaches us that the majestic, stable galaxies we see around us today, including our own Milky Way, were likely forged in the crucible of such violent, chaotic mergers long ago. This nearby wreck is not just a spectacle, it is a time machine allowing us to witness the very processes that built the modern cosmos. The brilliant superstar clusters are not the whole story. Among these glittering stellar metropolises, a quieter population seems to be absent. We see the giants, the colossal cities of stars, but where are all the small towns? This is the puzzle of the missing low-mass clusters. In a calm galaxy like our own, star clusters form across a full spectrum of sizes, from sprawling assemblies of a few hundred stars to the grand globular clusters containing millions. The violent merger of the antennae should, in theory, be creating a similar range. Yet our telescopes reveal a landscape dominated by the supermassive, with a curious scarcity of their smaller, more fragile cousins. So where have they all gone? The answer may lie in the brutal reality of this cosmic environment. a low-mass cluster held together by comparatively weak gravitational bonds is incredibly vulnerable. In the gravitational storm of a galactic merger, these flimsy structures are easily shredded. A single close pass by a massive gas cloud or another cluster can pull them apart, their stars scattered into the general galactic population like leaves in a hurricane. Their fragility gives them a short lifespan in such a chaotic neighborhood, but the violence may also be preventing their birth in the first place. The same immense shockwaves that trigger star formation favor the collapse of the very largest gas clouds, those with enough mass to resist being torn apart by the very turbulence that created them. It is like trying to build a house of cards in a wind tunnel. Only the sturdiest, most massive structures have a chance to stand. The conditions here may be so extreme that they naturally select for giants, producing an overwhelming number of superstar clusters, while the smaller ones are either destroyed quickly or never form at all. Could it be that every star we see in the future elliptical galaxy was once part of a small cluster that dissolved, its identity lost to the chaos? This missing population forces us to question whether we are seeing a true bias of nature or simply the grim efficiency of a cosmic demolition zone. The two brilliant hearts of the original galaxies now stare across a shrinking void. These are the nuclei, the dense central cores where each galaxy's oldest stars are concentrated, and they are performing the final, intimate steps of a gravitational dance that began hundreds of millions of years ago. They are not simply falling straight toward one another, they are in a tight orbit, whirling around a common center of gravity like two dancers spinning, hands nearly touching as they are pulled inexorably inward. This slow, spiral death is driven by a subtle but relentless force known as dynamical friction. Imagine each nucleus moving through the dense cloud of stars, dark matter, and gas that fills the space between them. As it plows through this invisible sea, its immense gravity tugs on the surrounding material, pulling stars and dark matter slightly toward it, creating a wake of enhanced density trailing behind. This gravitational wake, in turn, exerts a pullback on the nucleus, acting like a cosmic brake that steadily robs it of its orbital energy. This loss of energy causes the cores to spiral closer with each passing revolution, their dance tightening into a final, furious embrace. Within these cores, the gravitational environment is one of pure extremes. Stars are not following the stately, predictable orbit seen in a calm spiral galaxy. They are being whipped into frenzied, chaotic paths, slingshot around by the combined and conflicting pulls of the two nuclei. This creates a zone of unbelievable stellar density, a cosmic traffic jam of ancient suns where the night sky for any hypothetical planet would be a perpetual, blazing daylight filled with a mosaic of countless alien suns. This is the calm before the ultimate storm, the final act of consolidation that will forge a single, new galactic center from the ruins of two. What gravitational secrets will be revealed in the final, crashing moments of this billion-year duet? The final, quiet shape of this cosmic wreck is already written in the laws of physics. After eons of brilliant chaos, the two galactic nuclei will complete their slow spiral, merging into a single, new core. This final consolidation is the last act of the demolition, forging a stable gravitational anchor from the ruins. Without the fresh supply of gas, either expelled by galactic winds or consumed in the final firestorm, the engine of star formation will sputter and die. The brilliant blue blobs of young stars will fade away, their massive members having long since exploded. What remains is a vast, swelling crowd of older, cooler stars, their collective light shifting from blue to a dull, reddish gold. The magnificent tidal tails, the very features that gave the antennae its name, will slowly dissolve. Their exiled stars will either drift apart into the darkness or fall back toward the new center, their streams erased into a general haze. The galaxy transforms, smoothing out into a featureless, egg-shaped swarm, what astronomers call an elliptical galaxy. This is the ultimate fate of such a violent merger, a red and dead galaxy where no new stars are born, a calm and ancient monument to a wild youth. This future is not unique to the Antennae. It offers a profound preview of our own galaxy's destiny. Billions of years from now, the Milky Way and Andromeda will meet in a similar slow-motion dance, their collision likely creating a new, giant elliptical galaxy that astronomers have nicknamed Milkomda. The spectacular, chaotic wreck we see today in the Antennae is a glimpse of our own cosmic future, a reminder that even the grandest structures in the universe are not permanent, but are constantly being reshaped by the relentless force of gravity. From colliding black holes to runaway stars and dissolving clusters, this journey through 50 cosmic mysteries reveals a universe in constant, violent flux. The Antennae Galaxies are far more than a beautiful celestial snapshot. They are a living, breathing laboratory where the fundamental rules of galactic life and death are being written before our eyes. Every strange phenomenon, from the faint glow of light echoes to the invisible rain of cosmic rays, contributes to a grander story of transformation. We have witnessed how destruction fuels creation, how stellar deaths seed the cosmos with the ingredients for new worlds, and how the invisible hands of dark matter and magnetic fields orchestrate the entire cosmic dance. This single collision is a master key, unlocking secrets of galactic evolution that stretch from the ancient past to the far future, including the ultimate fate of our own Milky Way. So the next time you look up at the night sky, remember the incredible dynamism hidden within the stillness. Those pinpricks of light are not fixed, they are part of an endless cycle of collision, birth, and renewal on a scale beyond human comprehension. Which of these 50 phenomena reshaped your view of the cosmos the most? Let us know in the comments what cosmic mystery captured your imagination.